Okay, so today what we're going to discuss is an extension of the video I did on bubble sort. If you have not seen that video already, you should probably check that out before you watch this. This is an extension of our video on covering bubble sorts and an in-depth analysis of the exact comparisons and the exact swaps that the bubble sort algorithm does. So this is going to be an extension on that video, and we're going to discuss how bubble sort has the potential to run in linear time and what cases it would run in linear time. So before we get to that, what I want to first go through is what were the best, what were the worst, and what was the average case for bubble sort's runtime. So let's look at those cases right here. So the average case for a bubble sort is going to be an array that is sort of sorted, sort of not sorted. We're going to have to do some swaps. We will always do comparisons. We will do all our comparisons, but we might not always do swaps. For our worst case, we have an array in reverse sorted order. We are going to have to do all of our swaps, and we're going to have to do all of our comparisons. And then finally, for our best case, we have an array that is already sorted, and what we're going to do is we will do zero swaps. We're going to do zero swaps, but we're going to be doing the same amount of comparisons as the worst case and as the average case. We're going to be doing the same amount of comparisons. So there's something wrong with that. Why would we do the same amount of comparisons when we know that an array is already sorted? How can we improve bubble sort? So first I need to show you the inefficiency, and then once we see the inefficiency, we'll have the ability to draw a conclusion on how we can improve that inefficiency so that we can have the best case run in linear time. Okay, so our job is to improve the best case. We have the best case. This array is already sorted. The algorithm of choice is bubble sort, and what we're going to do is we're going to apply the raw bubble sort we had before. As always, the code is in the description. I have the code in the description for the optimized bubble sort, and on my other video, I have the code for the raw bubble sort, unoptimized for the best case. So what we're going to do here is we'll walk through this example. Bubble sort's job, I have I and I have j. I want to bubble up the item that belongs at position I, and once I'm finished bubbling up that item, I move I backwards, and then I place at here, and then I try to bubble up to here, and then I try to bubble up to here, and then here. So for each placement of I, I'm going to use j to bubble items up and do comparisons. So here's an example of the best case, and we're going to see how we can improve it to linear time. And again, the best case complexity before with the raw bubble sort we covered was O of n squared. And our job is to improve that to O of n. So let's walk through this. So for the first comparison, we're going to do a comparison. We will compare 1 and 2. We'll compare j to j plus 1. We compare j and j plus 1. The item at j to the item to the right of j. So is 1 greater than 2? Should I do a swap here? No, I should not do a swap, advance j. J is now here. I compare 2 and 3. Is 2 greater than 3? It is not, so we do not do a swap. Advance j. Now I compare 3 and 4. Is 3 greater than 4? 3 is not greater than 4, so I advance j. And now is 4 greater than 5? 4 is not greater than 5, so I advance j. And I want you to notice, we're in the first pass of the outer loop trying to make a placement up to I. And notice that we made zero swaps. And this is the best case. We will always make zero swaps. We will never swap. But notice that we never made a swap. We just did comparisons on the whole array, and we noticed that no swaps were made. So what does that mean? Let's just keep that in mind and let that simmer. So the next step would be we would move j back to the front of the array and move I one position backwards. I will end up here. And now what we're going to do is we'll start from j, we'll bubble up to I. And what we're going to do is compare 1 and 2. Is 1 greater than 2? No. Is 2 greater than 3? No. Is 3 greater than 4? No. And now we need to go put j back at the front and move I to here. Is 1 greater than 2? No. Is 2 greater than 3? No. And what we notice is we need to move j back and we need to move I over here. So, is 1 greater than 2? No. No swap. And what we do is we can't move I back a position because we'll be to the first item. And we're only going to move I as far back as the second position in the array if we're indexing off of 1. If we're indexing off of 0, index number 1. I want you to look again at this array, and I want you to notice something. What was the job of I? What was I's job? So let's forget about J, let's forget about bubbling anything up. We need to notice that 5 is already in the final position it's meant to be. Let's move I back 1. Notice that 4 is in the position it's going to be. No matter what we do, 4 is already in the sorted position. This is where 4 will end up. And again, 3 is already in the position that it's meant to be. And then again, 2 is already in the position it's meant to be, and that is it. So what we notice is that all of these elements are in the positions they know that they're supposed to be. But the thing is, our algorithm will not know whether the input is sorted in increasing order. It's not going to know whether it has this special case. So how do we bring this to linear time? So the key is we need to remember where our latest swap was. Where was the latest swap? This is the key question to improving our runtime to O of n. So let's do a quick walkthrough of what this would look like, and then I will explain the real understanding behind it and why it does what it does. So what we're going to do is we're going to have an I, we're going to have a J, and we're going to have a T. The T stands for the last position that we did a swap at. So if I swap 1 and 2, then I'm going to have T point to the left side of the swap. So if I swapped 1 and 2, T would be pointing right there. So if I swap 3 and 4, where would T point? So T is going to point to the left side of the swap, the item that was swapped. So T is going to point right there. T's job is to point to the last position that an item was swapped at. So now that you understand that, I think we are ready to look at how we can improve the best case time complexity to a linear time. Okay, so again, I want to say, if you have not seen my bubble sort video, it was a very in-depth video covering bubble sorts and the average, worst, and best case complexities and the exact number of swaps we'll do for each case. This is going to make less sense unless you've watched that. But if you have, this is going to be a good walkthrough and you'll have pre-context to understand this. So here is the pseudocode for this optimized approach, and I'm going to point out what we changed to give us a linear runtime for this algorithm on the best case, and we'll do a walkthrough. So what we're going to do is we're going to start I at the second to last position in the array. So the second to last position is where I stands, and we're indexing off of 1. So just keep that in mind, indexing off of 1, indexing off of 0. Be comfortable going between those. So the second position in the array is going to be right there. This is the second position, and that is where I is going to stand. So where we put J is, we're going to put J at the first position. And index 0 is going to be where J sits, or position 1. Remember, indexing off of 0 and 1, just keep in mind how we're working between those. So I just wanted to color that line because it's clear, because what is new here is this T. T is going to be right here, and I'll explain again what it does. Okay, so T's job is to show us the most recent position of a swap. It shows us the last swap in an iteration so that we know where to put I. If I know where the latest swap happened, then I know that everything past the swap was sorted because we did comparisons against what was past T, if that makes sense. So if we know where the last swap was, I know everything past that is going to be sorted because we did iterate over it and it turned out that it was sorted. No more swaps happened past this swap. So that is what T does. We're going to start T off at position 1. T stands right there. So what we're going to do is, we're going to do as we always do. But it's a little different here because we are going to try to bubble up an element to the position at I plus 1. So we want to place at this index. We want to bubble all the way up to here. So instead of J sitting at one position behind I, J and I can overlap. So that's the only small difference in this. We're not really changing our approach. So what we're going to do is we're going to go from 1 to I, and again, we have our comparison. We have our swap And if we swap, we remember where the swap happened. This is where we put J, where the swap happened, into T. T is our remembering. We remembered with T where the swap happened. So what we're going to do is we're going to do the bubbling up, and then once we're done bubbling up to this position after I, we're going to set I. And where do I put I? I put I one position behind T, because I need to start placing one position behind where I already know all the stuff past me is sorted because I compared against it and decided to do no swaps over there. My last swap was right here, not over here. So I can start I from here. So that's why we can start I from one position behind T. So this is the pseudocode for it. So let's actually execute the walkthrough on the best case, and we'll see how this turns into a linear time runtime. Okay, so this is where all our variables stand. We explain this and we put all our variables here. So what we do is we do as we always do. We compare 1 and 2. Do we do a swap? Is 1 greater than 2? 1 is not greater than 2, so I'm going to advance J. Okay, so 2 versus 3. Is 2 greater than 3? 2 is not greater than 3, so what we're going to do is advance J. Compare 3 and 4. Is 3 greater than 4? No, it's not. Advance J. And I want you to notice, T is still standing back here. The last swap is at the very beginning because we haven't done anything. This is the default for T. So if I were to do a swap here, T would pop over here. But T stays over here because as far as I know, all of this is sorted. As far as I know, all of that is sorted and T stays here. T is the division line basically between what is sorted and what may potentially not be sorted. So let's continue on. So we advance J. So is 4 greater than 5? 4 is not greater than 5. So what we do is we do not do a swap, and now we have reached the end of this loop, this for loop right here. So we exit the for loop because we just finished our iteration of J up to I on top of I, and what we do is we come down here, and now I need to make my decision. I, where do I put you? What is the next element to bubble up? Where is the division between what is sorted and what is potentially not sorted? So I becomes one position behind T. Where is T sitting? I did no swaps. This is the best case, and I move I one position behind T. So let's do that. So I want you to notice that I is now out of bounds of the array. I is now at index -1 or position 0. Remember, position 1, position 2, position 3, position 4, position 5, index 0, index 1, index 2, index 3, index 4. So remember indexing off of 1 and 0. It's just a small mental adjustment. Okay, now we see I is position 0, index -1, but let's just say position 0 to correspond with this. So I is at position 0. So we'll come back to the top of this while loop. I is at position 0, is 0 greater than 0. No 0 is not greater than 0, and what happens is I exit the while loop and we reach the bottom and we are finished. So what happens is we are finished and we declare this sorted. And notice how many comparisons we just did. I did 1 comparison, I did 2 comparisons, 3 comparisons, 4 comparisons. What is the size of this array? N equals 5. I just said we did 4 comparisons. So what does that say? That says that we just did n-1 comparisons because 5 minus 1 is 4. We're going to do n-1 comparisons with this optimized algorithm. This will still work for a worst case. It'll still work for an average case. It's actually faster in the average case, but not asymptotically faster. But we're going to do n-1 comparisons, and what does that become? That becomes linear in runtime. The n-1 turns into O of n because n is the upper bound on the work that we're going to do in terms of comparisons. So in the best case, this becomes O of n. So on Big O cheat sheet, when you see that the best case of bubble sort is O of n, this is why it is O of n in the best case. This is why before it was n squared because we would do all the comparisons and we weren't intelligent about where we continue placing from. But if we're intelligent about where we continue placing from, bubble sorts can have a linear time complexity in the best case. So this is the pseudocode, and that is how bubble sort turns out to have a linear runtime in a very specific case. So that is all for this video. If you like this video, hit the like button and subscribe to the channel. I know these videos are kind of off of like the kind of leak code route, but I still think it's very important to do algorithmic videos because these types of things are just as important as doing those raw leak code questions. You know, thinking about the exact number of operations a certain algorithm or problem does is very beneficial because it helps you really understand what's going on, and it helps you be able to analyze other problems more easily and efficiently because you know the steps to take. So that is all for this video. Thank you for watching if you have watched this far, and what we gotta do is